So I'm going to start with a very brief introduction, and then I'm going to switch to my iPad, which will disconnect my computer, but I should be able to join back on. And then I can share the screen so we can go through the thing. So yeah, so hi everyone, and welcome to the first real session of the SNARGs book reading group. So I'm Giacomo, I'm a PhD student with Ale. And today, as the plan was to go through like the part one of the roadmap that we talked about in the first session, which would be like talking about introducing a model, the random oracle model, introducing the object of this book, which are like succinct arguments in the pure random oracle model, and just put towards some definition that then we will be like using throughout the whole course, the whole reading group. So in general, during this whole thing, feel free to interrupt me and ask questions whenever you want. I think this really helps, and I think it helps also making things much more interactive. So feel free at any point to interrupt me if something is not clear or if it's something you have in your mind. So my plan is that I'm gonna now share my iPad. We're gonna be slowly going through like the main definitions. I'm gonna try to give you some context and some ideas over it, and then you can ask me questions, things which are like unclear, and we continue. Okay, does that make sense? All right.
Sounds good.
Yes.
Okay, cool. Then now I'll try to join with the iPad, and hopefully things don't break completely. Which there's also the chance, but hopefully it doesn't happen. Hello? Can you hear me now?
Hello.
Hey, welcome back.
Yes.
Amazing. Then let me share my screen. Okay. I seem to be wanting to broadcast. Can you see my screen now?
Yes, we can. Yes.
Amazing. Good. Okay, then let's start over it, just with a overall roadmap. Okay, so this is part one, which is going to be about like the basic model that we're going to be working on, which is the random oracle model. So in this part, we have like four main things which I will be going over through. So the first one will be the random oracle model, which is a very common tool used in cryptography. So we're going to be looking at the definition, some ideas about simulation, the difference between the random oracle and pseudo-random functions, validation, and then benefits and drawbacks. So this will just be really setting up terminology and then thing that we can use to talk about arguments later on. The next chapter will be about like some of the properties that this random oracle model gives you, which will be used later on. Then we will move to talk about knowing arguments in the ROM. This will introduce the syntax of the arguments and some basic properties. And finally, I think this should bring us almost close to the 1 hour mark. We're going to be talking about some basic observation about the arguments, such as error reduction, the flavors of adaptive and non-adaptive security, and then we'll just look at one pathological construction. Okay? Good. So let me start with talking about the random oracle model. So the random oracle model, the way I like to think it is that of a black box in the sky. So in general, in cryptography, there's a lot of notions in which a function with some certain feel of being random and looking random need to exist. And the random oracle is one formalization which allows you to model it in a formal sense. So in general, what you're trying to model, you're trying to model protocols which make use of an hash function which is ideal. So this in the sense that like every input is mapped to a random output. So if you think about hash functions that we know, like for example, SHA-256, we know that there's an algorithm which efficiently just gives like maps an input to an output. But for all intents and purposes, without evaluating SHA-3, do not seem to be able to find some relation between the input and the output, apart from the fact that they are connected by SHA-3. So there's some terms of unpredictability that without querying it, you don't get any visibility on what the output will be. So the output feels random. The random oracle formalizes this and working in this model allows us to do like very like nice security proofs. So, okay, let's start talking about what the ROM is. And again, feel free to really stop me at any point. So, how do we formalize the ROM? Well, the way that we formalize is that the random oracle is just a function which is sampled from the uniform distribution over all functions. So in particular, we have this notation U sigma for all of the functions which map arbitrary length strings into bit string of a given length. So in this case, the length that we'll have, we denote it as sigma. In the random oracle model, we say that what we end up doing is we sample one random function from this distribution. So this can be thought about like I assign one output to every bit string. There are different flavors. We're going to be seeing them later on, but in general, the modeling is really I just select one function, and this function will be the one that we will be working on for the rest of the protocol. Then what you'll end up doing is you end up having.
Can I interrupt?
Sorry?
Yes, please. Go ahead.
Could you zoom in a little bit? It's quite small.
Yes, like this is better.
Yeah, that's awesome. Thanks.
Or maybe I can also do. Let's see if this is better.
Yes, that will be better.
Yes.
Yes.
Let me tell you if this is all right.
That's way better.
Okay, perfect. Good.
And I wanted to kind of ask about this function that you just described, like the one that we are sampling. What it is like a set of rules that tell us for every single string, for every single like string of arbitrary length, there is some sigma length string that is the result of that quote unquote hash.
Exactly. So you can imagine that here what I'm really doing is I have like, so here is the set of all like 0, 1 string. Of course, it's an infinite set, but it is not too important. And then what I'm sampling the mapping that maps it to like, so maybe I say like the old 0 string maybe maps to like 1, 0, 0, 0, 1, 0, for example. So when I'm sampling it, I'm just deciding where all these mappings end up being.
A random length sigma string, right? Like because of u of sigma, we know that on the right side we're always going to get length sigma. On the left side, it can be any length.
Exactly. So this is a fixed length, and this is arbitrary.
And for each possible input, we are choosing a random output.
Yes.
Is that right?
So this is what we're doing. That's what we're doing in the formalization. Turns out that the structure is nice enough that you don't really have to pick this a priori. You can do something called lazy sampling, but we'll get to that later on. But yes, so intuitively, for each of these bit strings, I'm selecting one canonical, let's say, value, which will be a bit string of length sigma.
Why did you say canonical there? That confused me. Everything else you said.
Yes, I'm saying canonical because once I sample the function, once I sample f, the value, which one will be just one, it will be determined.
But yeah, I think what feels noteworthy here is that we are in the first place choosing a random output for every single input. In I guess we're choosing a function f over this space,
Yes.
and that has the effect of, it's like choosing a random f is the same as kind of choosing for every input what its output is. But and your
Exactly.
point is that once at f we lock it in, we're using that for the rest of our protocol.
Exactly. Once you sample, f is a deterministic object. It's just a table.
Thanks.
Good. Amazing. So yeah, we sample and we get this f. We use this notation for this sampling. And yes, each input will be mapped to a random output. But once the function is fit, this is what like our algorithms, like for example, the prover and the verifier, will be using jointly. Okay. So as I said, like each algorithm in this random oracle model will get access to this to the random oracle by definition almost. Hello, I heard some noises. I don't know if there was a question.
Hello?
Go ahead.
Hello?
Yes.
Hey, we
Yeah.
hear you.
So I was just asking, like, if let's say the star was 2 and another in case 3, what was the difference? Can you explain, like, I mean, the domain case doesn't have any particular this thing, right? For a fixed sigma, it could be anything.
Yes. So in this particular model, we have our functions that are able to take arbitrary length input. So the random oracle takes any kind of like length, so length 2, 25, more, whatever, and maps it to something of length sigma. Does that answer the question?
Yeah, okay.
Good. You could consider a formalization in which you consider like just random oracles with just, I don't know, look at like 2 or 3, some specific input length, but in this case, we just do arbitrary because it simplifies annotation a lot. Good. Okay. So you will have algorithms that want to like query the random oracle, and you cannot give the table to this algorithm because the table will actually be very large. The size it will have will actually be infinite. So instead, the way that we will do it is that the algorithm that will be considering it will have query access to F. So the algorithm will be able to make queries to the random oracle at the point that they decide. So you can think of this as the machine having a special instruction which specifies one input, so a query, and then in the next cycle it will receive an answer. And the way that we write this is we write this like this. So for example, here I'm saying that the algorithm A with input A, little a, and oracle access to F returns the value B. Okay. So
Excuse me.
Yes.
Can I ask a question too? If we forget for a moment about the size of the table, which makes it impractical to give to an interested party. My question is, won't it ruin the one-way property of the function? Is it important here?
Yes, in a certain sense, if you assume that, like, for example, suppose that the malicious prover got like as input the entire table, then it could run in time linear in that input because it would have the table and look at, for example, inversions and collisions.
So it is not a valid reason to not give out the whole table.
Exactly, but yes, yes, security would not hold, but the size, I think, for me, is the more poignant reason, just because it would be an infinite object. Yes, so
Thank
the
you.
soundness would not hold in that case, yeah. So just to give you like an image of what these things are, so you will have your algorithm A, which gets as input little a, and can make queries to this oracle F. So this will give you queries and answer, and at the end will output some value B. So this is the kind of like picture that you should have in mind at this point. Okay. So Oracle algorithms, they have Oracle access to like the random oracle. I'm using Oracle a lot of times in this phrase. I apologize. And he gets an input. He can make queries to the random oracle and get answer back to it. So in particular, he could, for example, query the random oracle at X and receive the value Y back. And depending on this value, you can decide what B to output. Okay. Let me move to the next part, and then we can like talk about the random oracle model. And roughly, the random oracle model will be a model in which every party, so honest and malicious, are oracle algorithms that are given query access to the same function, which will be the random oracle. So the picture that you should have in mind here in this case is that every party might be prover verifier. There might be other settings that you're interested in. We'll have like we'll be interacting with each other, but also have access to this random oracle, which will be which will have been sampled from this distribution U sigma. And this is really all that the random oracle is. The random oracle model is. So it's a model in which every party in the interaction, honest and malicious, has access to the same shared function F. Okay? Later on, when we'll start seeing like some kind of definitions like of arguments, we'll see like how this impacts, for example, completeness and soundness. Okay? And the thing which I want to also stress is that in the random oracle model, everyone has access to the same random function.
And for like thinking about this in real context, that shared function might be something like SHA-256 or SHA-3, right? Like that is the hash function, and those were
Yes.
selected from some random sample.
Exactly. We'll talk a bit more about what the realization will be later on, but yes, you can think of it as that the parties will have agreed on some hash function.
Cool.
But in the model, it's just a random function. I will talk a bit more on that. Okay. In this book, the kind of like notion of security that we consider are that of security against like bounded queries adversaries. So in this setting, like you have like, say, for example, I'm going to just jump the gun a little bit, say that you have like some prover who's trying to convince a verifier with some proof, pi, and the proven verifier will have access to a random oracle F. The kind of the flavor of definition that we will have is that the prover should not be able to convince the verifier of something false. Ooh, wrong. Without making more than a certain number of queries to the random oracle. So here there will be at most, for example, T queries. So the setting that we will have is that the adversary has bounded queries. So we do not care how fast it runs. We don't care about anything else. It just won't be able to make too many queries up to the random oracle. And we'll use the letter T to denote this adversary query bound in general. So whenever we talk about a T query adversary, this is an adversary you can make at most T queries to the random oracle. This setting is also sometimes referred as the pure random oracle model. and everything that we're gonna do in this book will be in this pure random oracle model. So when I say we're proving it in the ROM, we're gonna be proving everything in the pure random oracle model in this book. Okay. Question about the bounded query model? Okay. Good. So, okay, we're basically almost done with introducing the ROM. I'm going to introduce some more notation that we're gonna have to use later on. So, in particular, something that we'll be doing a lot in this book will be to analyze the query answer trace. So, we're gonna be using this notation, and what do I mean by the query answer trace? So, the algorithm A will run, and we'll make some queries to the random oracle. Maybe you will query Z1 and get a value Y1. You will query Z2 and get a value Y2, and so on. The query answer trace will be just the ordered list of all these query answer traces. Let's say ZT and YT. So, okay. So the query answer trace is just all the queries that the adversary has made to the random oracle. And this will be important for various reasons. So I just wanted to introduce this notation so it's not unfamiliar later on. So just to evidence it, we just put a little TR in front of the arrow. Good. Okay. So as I said before, the random oracle is not an object that can be efficiently sampled as an entirety. It's an object of infinite size, which makes it very hard to deal with. So in fact, what you can do though is you can you can have efficient algorithm which efficiently emulate the random oracle. This is called lazy sampling. What's the idea of this? The idea is that the algorithm can just whenever somebody wants to make a query to random oracle, it can just sample a new random string and then just remember which random string has been sampled. And this will give you a distribution which is exactly the same as first sampling a random function and then using that. Only now an efficient algorithm can take care of this. So why is this important? So this is how the algorithm would look. So initially you will start by setting an internal state to be an empty mapping, and then you just do a lookup. So if to answer a query, if you already contain the key, then you return the value that you have set. Otherwise, you just sample a new uniformly random string and update the state accordingly. The reason that this is important is that the random oracle has a simple structure, and it will be a very important thing in some security reductions. In the paper, we'll mainly focus on the results rather than the security proof. But anyways, lazy sampling is such a fundamental tool that I think is important to at least mention it in this introduction. Okay. So here I'm just saying look, I have I want to have an efficient algorithm which simulates a random oracle. How can I efficiently implement one? And the way that I do it is just by lazily answering queries by sampling random strings when needed, instead of pre-computing the enormous table, which would not definitely fit in any efficient algorithm memory. Okay. Okay, let me now talk a little, I'll just spend a second about the difference between pseudo-random function and random oracles. So if you're familiar in cryptography, there is this concept of pseudo-random functions, which are functions which are hard to predict. These are used in a variety of different contexts, and at an high level, they might seem to be filling a very similar role to that of the random oracle. So one natural question that one might have is, why don't we like use these primitives in order to realize the random oracle? And the high level, so if you look at like what the definition of a pseudo-random function is, it basically tells you that the pseudo-random function, which we denote like this, is statistically close to a uniformly random sample function. So, so in a certain sense, a pseudo-random function is defined to mimic as much as possible a random oracle. The issue is that turns out that these security guarantees are only given when the description of the pseudo-random function remains secret. This is distinct from like the setting that you have in the random oracle, because the random oracle instead requires that every party has access and is able to evaluate the function itself. So we cannot rely on the security of pseudo-random function in order to realize random oracles, because since everybody has to be able to evaluate the function, the pseudo-random properties will not be able to like give you security. Okay. Okay. Okay, now I'm gonna just talk about, so before we talked a little bit about like how to instantiate, so how does practically the random oracle model lead to real world protocols. And we talked about before about this idea that you can like concretely you can take a protocol P that uses a random oracle and replace it with some other function G. So the picture that I have in mind is that you will have like a protocol P that would usually query the random oracle, and now you're like replacing it with like some new other protocol, say P prime, that whenever it wants to query random oracle, it will instead run some function G, and this G is some function like say chef free or like Blake free, or pick your favorite hash function. So you're just replacing wherever a query to the random oracle is done was made to another function G. So this process is called heuristically instantiating the random oracle in the cryptographic literature. The issue is that in general, it does not inherit the security proof of the ROM, because the function G that you're using it will not be a random oracle. It cannot be a random oracle. It's an efficient computing function. It's not an infinitely large table. So the new protocol does not may have no proof for its security. What the random oracle heuristic says is that in general, if you do this process, you actually arrive to some new protocol P prime, which will actually be secure as long as G is a sufficiently strong hash function.
Excuse me.
Yes.
Could you say a word or two about if this SHA-3, for example, is a pseudo-random function, and how it plays out with the previous highlight?
So
Before this,
SHA-3 by itself is not a pseudo-random function because it has a description, right? If I tell you like there's no secret thing involved, so there's no unpredictability. If I tell you like that I'm using SHA-3 and I'm out and I want to hash the old zero string, I already know what the value will be. It will be the output of SHA-3 on the string. You can make it into a pseudo-random function by then maybe sampling a secret key and taking an hash of a secret with your input, for example. But then this key needs to be kept secret. So, for example, people would not be able to. So, SHA-3 by default is not a pseudo-random function in the terms that I was talking beforehand.
Thank you.
No worries.
I have a question, if it is possible.
Yes.
About
Could you speak a bit louder? Like you're very, very quiet.
Okay. Can you hear me now?
Yes, slightly. Yes.
Okay. So I have a question about the example you give about G is the SHA-3. So by the definition of G is 0, 1 star. So 0, 1 star is infinite. So I don't understand because SHA-3 is from a finite set to a finite set, and here we have G from infinite set to a finite set.
So that's not an it is an infinite set, but like every entry in that domain is a finite string, right? It is the set of strings of any length, but every single string itself is finite.
So but if you fix the length, so you will have a finite set. You cannot, for example, let's say the 0, 1 star is at most length n. So this is a finite. This set is finite because if you fix the length, so you cannot go more than 2 to the n. I don't know. This is my understanding.
Yes.
Maybe I am confused.
No, you will be able. So basically, what I'm saying here is the efficiently computable function. I will give you like a string of some number of bits, and then I want to output a digest. And the number of bits in the input will still always be finite because all of the algorithm that we talk about only give finite input. And in fact, the way that we define the model, we only allow F to receive input of finite size. Now, most of these hash functions like SHA-3 and Blake-3, they're often defined for like fit size inputs. But usually it is possible to like by maybe doing hashes of hashes or compressing to be able to handle inputs of arbitrary length. And that's usually what we do.
Okay, thank you. I get it. Thank you.
No worries. Good. Yes. So, okay. So I said that the heuristic is gives you a protocol which is heuristically secure as long as the hash function that you're using is good enough. And now this, of course, begs the question of what kind of an hash function would be good enough. And so there will be a few properties that are at the minimum needed. So we will see them in the next chapter, but for example, we need a random oracle is inversion resistant. I'll define it later, what exactly this means. It is also collision resistance and prefix resistance. So in particular, for a function to be a good instantiation for like the random oracle, there might be a lot of you would like at minimum this property to be satisfied. So in particular, collision resistance should happen, inversion resistance, and so on. This is not enough because still, it won't be a random oracle, but usually functions which satisfy these properties and they do not have attacks that are better than like generic attacks tend to be good candidates to be realized in the random oracle. In particular, two like hash function used in practice that are good realization of the random oracle are things like SHA-3 and Blake-3, for example, which also have the added benefit to be quite quick to evaluate. Okay. Good. So I think now I'm going to move in some of like the properties that the random oracle ends up having. And these are three properties that I was talking about before, which are unpredictability, inversion resistance, and collision resistance. But maybe before I dive into it, are there other questions about the first part where we were like defining the model? Okay, good. Then I think we can like start talking a little bit about some of the properties that the random oracle gives you for free. So, as I said before, one of the motivations for introducing a random oracle is that we want some notion of unpredictability. We want some function that if it is not queries, the adversary is not able to predict what the output will be. And this is in particular is fundamental for like something like Fiat-Shamir, for example, which we will see you will hear a lot more about in the following lectures. So this can be formulated like as the prediction problem. So you can consider like the problem like you're an algorithm. Say you're an algorithm A that gets query access to the random oracle. A wants to output some pair xy such that f of x is equal to y, but without querying it to the random oracle. Okay. Intuitively, the reason why this will be hard is because the random oracle is a random function. So you have each point is independent of all the others that you've queried. This, for example, would not be the case if the random oracle was a polynomial. Then by like querying a few points, you would be able to learn the value of the random oracle at every point. But since the random oracle is a random function, you won't be able to do that. And in the following lemma, we basically formalize the intuition. So I also wanted to take this occasion to like just introduce some of the notation that we use a lot in the book. So, okay, this lemma 3.1 formalizes this unpredictability notion. So we use this notation where we have like a bar, and then the things which are on the right side of the bar denote like the security experiment. So in this case, we've done two things. We have we started by sampling a random oracle. You see this a lot in the book. So this is the experiment in which we first sample a random oracle, and then we run the adversary A with access to the random oracle, and this will output a query answer pair xy and a trace. What we have the probability at which the adversary wins the game, which is this probability here. So we say that the adversary. Okay, let me actually do this. The adversary will win the game if he outputs x and y, which satisfy the condition in the left-hand side of the probability statement. And what we like, what this lemma says is that this will happen with a small probability. In fact, this is basically saying that the adversary cannot do better than just guessing what the string will be. Okay? So in general, in all of this book, we'll have something like probability, we'll have an experiment on the left, and here we will have some condition, which holds on the random variable sampled in the experiment. Okay? I don't want to go too much in the proof. Like I think talking about the properties is more important. But I just wanted to set out a notation so that you can like you can use it in the next reading group sessions. Okay, question about this notation and this unpredictability property? Okay, great. Then I can continue. So the first thing that we saw is that a random oracle is unpredictable. The next like property that you get is that the random oracle is also inversion resistant. So here we consider the following problem. So you have an algorithm which which has query access to some random oracle, and is given as input some target y. So the setting is the following: you have the algorithm A, which has query access to the random oracle. I'm drawing this picture a lot of times. So this is F, and you get as inputs some y. The adversary wants to find some x such that f of x is equal to y. So roughly, you want to find something that maps the random oracle maps to y. So you're first given y, and then you're trying to find the corresponding x. Intuitively, since you have no structure, the best attack that you can make is just to try many times until you get something which maps to y. So we show that this attack works, but yeah. But in fact, the random oracle satisfies this problem. Sorry, yes. So the strategy of like trying all of the trying a bunch of points until you find an inversion works. But we show that this strategy is basically optimal, that there's nothing better than you can do. And this is formalized in this lemma. So again, what's the game? So the game is the following. So you have like, you have your sample random oracle, and then you have an adversary which queries it. You want that for every target y, the adversary will not be able to query some point x such that f of x is equal to y. So in particular, the probability will be this, which is roughly the number of queries that the adversary makes divided by the number of divided by the output side of the random oracle. So the adversary can try a bunch of times, but it cannot really succeed with probability better than the trivial attack. Okay. All right. So this shows that exactly that the random oracle has this property of being inversion resistant. Okay. Next, what we will see is that the random oracle satisfies a stronger property still, which is that of collision resistant. So in this case, your goal as an adversary is to find two different function strings x and x prime that end up mapping to the same output y. So x should be different than x prime, and f of x should be equal to fx prime. Okay? Again, here there's a very natural attack that you can do, which is again just find a lot of points and then try to find a collision between them. And the analysis of this is what's called a birthday bound. So you end up getting like some quadratic dependency, and we show that this is basically the optimal success probability of an adversary. So in particular, yes, this lemma 3.1 essentially tells you that the collision that a random oracle is collision resistant. So again, I'm doing this thing a bit slowly just to get you people acquainted with the notation, but so the experiment is always the same. You first sample random oracle, and then you have an adversary, and now its goal is to find one of these collisions. So the adversary wants to find some pair S and S prime with the same with the same y, but with distinct S and S prime. And what we end up like just seeing is that the probability that the adversary is doing that is bounded by a term which is this term, which roughly you can also approximate as t squared divided by 2 sigma. So the adversary, if the adversary which does so an adversary which is bounded by t queries will have at most this success probability. This shows you that the random oracle is collision resistant. Okay, amazing. These were just basic properties of random functions. If you have questions, I'll go over them. Otherwise, we're going to start introducing arguments next. Okay, let me move towards them. So, okay, now we want to start. Sorry.
Is there any difference with hash functions which are also collision resistant?
So the notion of the definition of collision resistance is the same. So in collision resistance, you also want to forbid this. You want it to be hard to find distinctive values which map to the same image. But the main difference is that a collision resistant hash function is not a random oracle. It's just an efficiently computable function. So there's no concept of querying it. There's no concept of that. It's just a function that you can run. In this case, we are showing that a random function also satisfies this condition. So the difference is really that here we have like an oracle, something which is very large, while in the case of collision resistant hash function, you instead have like a very short description of the function that you're trying to find collision. But the property in itself is exactly the same. Okay, I'll go ahead if that's answer your question. Okay, so we'll be introducing like the concept of argument, which is what these books try to construct. So this book wants to construct argument in the random oracle model. And I'm going to just be talking about non-interactive arguments, which anyways is what people are usually more concerned about. So in the ROM, we have like the following picture. We have a pair of prover and verifier. The prover and verifier, they're both in the we're both in the random oracle model, so they get access to the random oracle. The prover gets as input an instance and a witness, queries the random oracle a bunch of times, and then eventually outputs a proof. On the other hand, the verifier only gets as input the instance. He reads the proof from the prover, and then will output one bit, either 0 or 1, depending on what or if the prover's proof has convinced him. So we will see that we want these arguments to satisfy some notion, which are completeness and soundness. So informally, in completeness, you want that for every, so these arguments are defined for a relation. You think of these as being like your run-of-the-mill NP relation. It could be like I know some solution to some mathematical equation. In this book, we're not really concerned of what this relation is. Just imagine that this is like the relation R is just a set of instance witness pairs. And the verifier just wants to decide whether some witness instance pair is in the relation or not, without having access to the witness, but only to the proof. In completeness, we say that like if the claim of the verifier, so of the prover, so that the instance witness is in the relation, then the honest prover will output some pi, such that the verifier accepts with probability 1. So in the honest case, the verifier will accept. in the soundness case, instead, if the instance is not in the relation, then every malicious argument prover, no matter how smart and powerful it is, will be able to convince the verifier to accept with at most a small error probability. And in general, we will have that the only restriction we will make on this on the malicious prover is that it makes at most T queries to the random oracle. Okay, so this is the intuition. So in the completeness, we wanted in the honest case the verifier accept, while in the malicious case, for a false statement, the verifier will not accept unless with some small probability. And so now we're gonna just formally define these things. In the experiment term that you guys have seen, that you've seen beforehand. Okay, so we say that an argument has a perfect completeness if for every instant witness pair in the relation, the following experiment outputs one with probability 1. So first, we sample a random oracle, as always. Later on, the prover, the honest prover, using the instance as a witness, generates a proof. And we want the probability that the verifier accepts that proof while given query access to the random oracle is 1. There are variants of this where you can allow like some non-perfect completeness, but for most of the arguments that naturally come up, you end up having a perfect completeness. Okay. Now, for soundness, there are two different like definitions that one can consider. One simpler and one more complicated. So one weaker and one stronger. So the first notion that we consider is that of non-adaptive soundness. Okay, what's the experiment over here? Well, so you have some instance which now is not in the language of the relation. So in particular, this is a false instance. And you're saying that for every T-query malicious argument prover P tilde, the following experiment outputs 1 with small probability. The experiment is, as always, you first start with the sampling a random oracle, and now the adversary tries to generate a proof by querying the random oracle. We want that the probability that the verifier accepts in this case to be bounded by some error, epsilon arg. So not in particular that we make the error depend on 3 things. One of them is the random oracle. See the seed length of the random oracle. Then on the query bound, and also on the instance. Okay. So different instances might have different errors, but in this case, we also add it in the error. Okay. What's the difference between non-adaptive and adaptive soundness, which we introduce next? So the experiment is basically the same. So you have your T-query malicious argument prover. But in this case, the prover is allowed to choose the instance after it has seen the random oracle. So in particular, in the experiment, you still have the usual part, but the prover ends up like choosing the instance pair on which he wants to convince the verifier after it has seen the random oracle. While before, if you look at the previous definition, the instance was fixed no matter what the random oracle was sampled. And apart from that, the experiment is the same. You want to bound the probability that the prover outputs some false instance, which makes the verifier accept. We also bound the size of the instance, but it is mostly just for parameters. So again, we will have our error, which depends on three things now, which is the oracle seed length, the query bound of the malicious prover p tilde, and the instance size bound. Right, and this definition is stronger than one that we saw before, because the adversary gets more power. The adversary is able to select the instance before, after seeing the random oracle. Well, before he already was committed in choosing the instance beforehand. Okay, questions about this? Okay, this is just the usual definition of completeness and sound that we've seen before. And again, this is like the kind of picture that you should have in mind, drawn in a better way than what I had before. The prover and the verifier, they interact while both having access to the random oracle. In the book, for pedagogical purposes, we also have like interactive arguments, but we will not be I will not be talking about them right now. Good. Okay. Question about completeness and soundness? Okay, let me go to the next part I want to talk about. Yes, so we have some efficiency measures that we will be considering it in this reading group, and the three main ones are the following. So we have the prover cost, the verifier cost, and the communication. So in both cases, the prover and the verifier cost, since they're Oracle algorithms, they will have two parts. They will have the running time and a number of queries that they make to random Oracle. For concrete realization, we will want this to be very small, because the number of the running time, of course, because you want the prover to be running in small time, while the number of queries will translate to the number of hash function call that we need to do in the concrete argument. So we want this to be small. Further, we would like to have there will be a message, which is the proof sent from the prover to the verifier, and we do not bias the size of the thing, which is another thing that we want to minimize. Now, I see that it's already 7 o'clock, so I can either stop now or continue. I'm not sure exactly how we want to do this. I think today was meant to be a section about a bit of bike shedding, putting a bit of the initial terminology in place, so that we can later on we can just not have to be bogged down into details and just talk about the properties of the construction that we'll have. But if you have questions or you want to continue, we can do other things.
Yeah, I think questions super welcome. I also and I think sort of in terms of content, this is a good place to wrap up. You could also maybe spend a few minutes doing a recap. Since you covered a lot of new information, if there's things you wanted to highlight in the last few minutes, that could also be a good use of time. And during that time, people can hop in with questions.
Yeah, that sounds great. So let me go back to the top, and then yes, and then I can just recap a bit what we've seen today. And feel free to ask me everything about the questions. So yes, as a small recap, so in this first session, we've been starting to introduce what the random oracle model is, which will be the model in which we will be operating in for most of this reading group. We talked about definitions. We talked about differences from other common non-cryptographic objects, such as pseudo-random functions. And we talked a little bit about like the realization of like the random oracle by heuristic instantiation, which is what ends up giving you like efficient arguments in practice. Then we went to look at basic cryptographic properties that the random oracle gives you as a random functions. Namely, the three main ones that we looked at were unpredictability, inversion resistance, and collision resistance. Finally, we've talked about arguments in the random oracle model. We've introduced the notation for non-interactive arguments, some of the classic efficiency measures, and yes, which this will be what we'll be aiming to construct via like construction like Micali, Killian, VCS in the next sessions. Now, what I would suggest is that now, before the next session, you start having a look at some of the things that we talked about, get a feel for the definitions. There are some notions which I haven't talked. So I've talked about completeness and soundness today. There's also knowledge soundness and dual knowledge, which I have not covered, but which I think are interesting for more advanced applications. There's this chapter 6, which is about basic observation about arguments, which talks about a lot of like interesting things. So for example, how to reduce error by repeating the protocol, some fine-grained differences between adaptive and non-adaptive security. It has this very small, very pathological like element of a fully secure like argument for any relation with super small proof size, as long as you allow a very inefficient prover. And he has this very cute lower bound on argument size, which I think if you're interested in these kind of things is a very nice little chapter. But yes, going forward, I think just having a look at this, getting familiar and acquainted with these definitions would be a good like use of your time before the next reading group session.
Can I ask
Any
a question?
Go for it.
Go for it.
Can you please explain again where is the adaptiveness on the non-adaptive soundness definition?
Yes, absolutely. Let me go back to it. This was it. Okay. Okay, so this is in the non-adaptive case. If you look at the quantification, the adversary is not able to choose the instance. The instance is given to it. It is instance X that we have here, and it is not able to pick an instance that it likes. So, for example, you could imagine that maybe in some like there are some random oracles for which some instances are like easier than others. In the adaptive case, instead, if you look at the experiment, and I don't know, it would be good if I could put them side by side, but I don't know how to do that. If you look over here in the adaptive case, the adversary is able to choose which instance he wants to use. So that's where the adaptivity comes in.
Okay, so that's all.
Yes.
It's the option of the adversary to choose the instance.
Exactly.
Okay, thank you.
No worries.
So which
Am
one
I
is
correct?
stronger?
Sorry?
Which one is stronger?
The adaptive definition is stronger because you give the adversary more power. So you give the adversary the power to choose the instance. So in practice, you want to have an argument with adaptive security. If you're familiar with like some of the issues that happen with like Fiat-Shamir transform, a lot of them is because the way that the implementation were made, they did not have adaptive security. They only had non-adaptive security. And that led to real-world attacks. So for most applications, you want to have adaptive security.
Thanks.
Good. Let me go back to the...
I just wanted to detail a bit if this adaptive versus non-adaptive basically the same as non-interactive versus interactive. arguments for the arguments?
And there are a bit of different notions. They're orthogonal. So you can have adaptive non-interactive arguments. You can have adaptive interactive arguments. You can have non-adaptive non-interactive arguments, and you can have non-adaptive adaptive non-interactive arguments. Like they're distinct. Like this is more about against which kind of adversaries the argument is secure.
I see. It would be nice to see kind of example or something. I don't know today, or maybe not today, or maybe it's a homework. Yeah.
Yes.
But
In fact, if you look at this 6.2, there you'll see an example of an argument which is which has non-adaptive soundness, but it doesn't have adaptive soundness. So you can see. And also it shows you how you can get like any adaptive security, any adaptive argument, and turn it into one which is adaptive. So sorry, a non-adaptive to adaptive. So 6.2, I think, is a good place to look if you want to get a feel about this distinction.
Yeah, I will pick into it. Thank you.
Hello.
Yes.
Yeah, so I just want to know like real life things like hello, plonk that are there. How do these concepts help us there? Like, I mean, how do they manifest in like whatever people build these days, like these concepts? Like,
yes. So, this particular book talks about these arguments in the pure random oracle model. And these actually lead to a lot of systems which are currently deployed. So, for example, if you think about things like SNARGs or Plonky 2, Plonky 3, RIC0, StatSynth, all of these kind of like tools that people are using, they can be thought about as being arguments of the kind that you've seen today. So you can like think of they're exactly like arguments in this pure random oracle model. So what we are like doing here, we just formalizing like a framework for analyzing this kind of arguments. So this leads to like, yeah, so if you want to like look at the security, for example, and the constructions of the of arguments like SNARGs, then this tells you how you can use how you can compile the main building blocks of SNARG, which are this thing called the interactive oracle proofs, into an argument. And you'll see this in practice later on in the reading group. I think it's part 5, but I might be wrong.
cool. Thanks.
No worries. Good. Any more questions? Okay, cool. So if we don't have any more questions, like I think we can wrap it up for today. I believe that the recording will also be online, and feel free to ask questions in the Discord channel. I'll try to have a pass and answer them. And I think we're meeting again next week at the same time, I assume.